Chapter 14.5 Testing the significance of the slope of the regression equation. The last set of procedures we'll examine in this chapter is to test the significance of the slope of the regression equation. Figure 14.17 shows exam grade data for another group of students, along with the regression line that best fit the data. Notice that this regression line is horizontal. A horizontal line has a slope that is equal to 0, as the figure shows. I'll be very surprised if interpreting the meaning of a slope of a 0 didn't appear in your next exam. You can count on it in my classes. So let's take a minute to examine what it means in our example. According to figure 14.17, the regression equation is y cap equal to 84 plus 0x. This means that for any value of x, y cap will always equal to 84. No matter how much a student studies, the predicted exam grade is 84 because the slope equals 0. Under these circumstances, we can conclude there is no linear relationship between the dependent and independent variables. Increasing your hours of study will not increase your exam grade. This would be very unsettling for me as a teacher. In our original exam grade example, the value B1 equal to 4.1786 represents the regression slope for a random sample of 6 students that was collected from a larger student population. This population has a regression slope B1 that is unknown because we have not gathered data on every student who took the exam. We can, however, perform a hypothesis test to determine if the population regression slope, or B1, is significantly different from 0 based on the sample regression slope, or B1. This test uses the following hypothesis statement. Null hypothesis, B1 equal to 0, or there is no linear relationship between hour of study and exam score. Alternative hypothesis, B1 not equal to 0, or there is a linear relationship between hours of study and exam score. If we have enough evidence from our sample to reject the null hypothesis, we can conclude that there is a significant linear relationship between the dependent and the independent variables. To test this statistic for this hypothesis test uses the t-distribution and is shown in equation 14.19, where B1 is the sample regression slope and capital B1 is the population regression slope from the null hypothesis. SB is the standard error of the slope. If you are anything like my student, I imagine that you are getting sick of all this standard error, but bear with me one last time. The standard error of the slope, or SB, measures how consistent the slope of the regression equation B1 would be if several sets of samples from the population were selected and the regression equation were derived from each of them. Each samples selected from the population will most likely have a different value for the slope, or B1. The $64,000 question is how close will this slope be to one another? Figure 14.18 shows the effect of small and large standard error of slope. Each of these 3 regression lines shown in the 2 graphs represent a separate sample taken from the population. A smaller standard error of the slope increases the likelihood that we can establish a significant linear relationship between our two variables. Enough talk about this latest standard error. Let's calculate. The standard error of the slope, or SB, can be found using equation 14.20. To calculate SB, we need to use the following data from earlier in the chapter. The calculation for the standard error of the slope are shown as follows. Now we can finally calculate our test statistic for the hypothesis test using the following data. To find our critical t-score, t alpha divided by 2, for this hypothesis test, we look at table 5 in Appendix A. This test also has n-2 or 6 minus 2 equal to 4 degrees of freedom. For alpha equal to 0.05 and a two-tailed test, the critical t-score is t alpha divided by 2 equal to 2.776. Because t is equal to 2.94 is higher than t alpha divided by 2 equal to 2.776, we reject the null hypothesis and conclude that the population regression slope is not equal to 0. This result provides support that a linear relationship exists between the hours that students studied and their exam grades. Figure 14.19 illustrates this hypothesis test. We can determine the p-value for this two-tailed hypothesis test by using Excel t.dist.2t function, which was introduced in Chapter 9. P-value is equal to t.dist.2t inside parentheses 2.94, 4 is equal to 0.0424. Because this value is less than alpha equal to 0.05, we can reject the null hypothesis. The following is the final topic to close out this example. Recall that B1 is equal to 4.1786 is the slope for only the 6 students from our sample, and that the actual population slope B1 is unknown. We can develop a 95% confidence interval for B1 using our sample with equation 14.21. The critical t-score, t alpha divided by 2, for this 95% confidence interval uses n-2 equal to 6 minus 2 equal to 4 degree of freedom. Looking at table 5 in Appendix A, we find that this result is t alpha divided by 2 equal to 2.776. Recalling that the SB equal to 1.41, the confidence interval calculation using equation 14.21 is shown as follows. We can describe this confidence interval with the upper confidence limit, or UCL, and lower confidence limit, or LCL, as follows. UCL equal to 4.1786 plus 3.942 equal to 8.121, and LCL is equal to 4.1786 minus 3.942 equal to 0.237. Based on our sample of 6 students, we are 95% confident that the true population slope is between 0.237 and 8.121 exam point. In other words, we are 95% sure that every additional hours of study will increase your exam grade somewhere between 0.237 and 8.121 point. Because this confidence interval does not include 0, we have supporting evidence to conclude that there is a linear relationship between the hour that students studied and their exam grade. One last look at the regression output in Excel shown in figure 1420 shows that the standard error of the estimate, or SE, is 4.32. It is found under the regression statistic heading and is circled in red in the very last row of the ANOVA table in this figure. We find the standard error of the slope, or SB, it equals to 1.41 and appears under the standard error column in the red box. The calculated t-score, 2.96, is located under the t-stat column, whereas the 95% confidence interval for the slope, 0.258 to 8.102, can be seen under the lower 95% and upper 95% column, respectively. The slight discrepancies from our manual calculation are due to rounding differences. Also, Excel provides the p-value for the significant test of the slope, which equal to 0.0417. Because we have a two-tailed hypothesis test, this value represents the area to the right of t equal to 2.96 plus the area to the left of t minus 2.96. We can determine the area to the right of t equal to 2.96 with Excel t.dist.rt function, which is shown graphically in figure 14.21, equal to t.dist.rt inside parentheses 2.96, 4 is equal to 0.0206. Because our p-value equal to 0.0416 and it is less than alpha equal to 0.05, we can reject the null hypothesis. Notice that the p-value for f-test that we perform in section 14.3 and the t-test are identical. This occurs because we have only one independent variable, or hours of study, in our regression model. When we consider more than one independent variable in chapter 15, this will no longer be the case. Thank you.